Welcome to Chem 652, Organic Chemistry 2. Today we're going to talk about aldehydes and ketones, and this is a continuation of a discussion we've already started. To remind ourselves, aldehydes have the following formula, where we have a carbonyl attached to an organic group, an R group, but also attached to a hydrogen. This would be an aldehyde. Ketones, on the other hand, have two different R groups, one attached to either side of this carbonyl carbon. They can be, but don't need to be, the same. So those are aldehydes and those are ketones, and we cover them together and treat them together because they structurally are so closely related, and also because chemically they have many of the same chemistries. What we're going to do today is we're going to explore reversible chemistries of aldehydes and ketones. Now, we emphasize reversible because these reactions are completely reversible, and as we work through the mechanisms we'll see that. But also because there's another set of reactions which are irreversible, and we'll cover those a little bit later. So aldehydes and ketones undergo both reversible and irreversible reactions, and today we're focusing on the reversible types. The simplest we covered already, and that is called a hydration reaction. The hydration reaction is not a particularly useful reaction. It's not synthetically useful, but it's an important reaction to learn because it teaches us some of the fundamentals about how aldehydes and ketones behave and how they react chemically. So we're going to go back over the hydration reaction, even though we already covered it once. It turns out that hydration can take place under either acidic aqueous conditions or under basic aqueous conditions. The next reaction we're going to study after hydration is so-called acetal formation. And this one is going to have to take place under acidic conditions. The mechanisms of these two reactions are very closely related. Unlike the hydration reaction, the acetal forming reaction is synthetically useful, and we'll look at some specific examples where we can put that to good use. And although we won't get to it today, coming up soon will be both enamine and imine formation. So these are our key reversible reactions involving aldehydes and ketones. Hydration, which is not synthetically useful. Acetal forming reactions, which we run under acidic conditions, and enamine and imine forming reactions, which we also run under acidic conditions. So let's get started. Let's look at these hydration reactions. Now, because aldehydes and ketones are so closely related, it doesn't really matter which one we pick. In class recently I chose an aldehyde, so I think this time I'll choose a ketone. And once again, those R groups can be but don't need to be the same. Now, what we know is that this carbonyl group is one, which is a little bit different than an alkene functional group, for example. Although there's a double bond present, one of the atoms that participates in the double bond is oxygen, and it's more electronegative than carbon. And consequently, this resonance form, which would not be a reasonable resonance form for alkenes, is reasonable for carbonyl compounds. What I've done is I've taken the pi electrons and I've placed them completely on the more electronegative oxygen atom. Again, we wouldn't do this if it was a carbon-carbon double bond, because those would be two carbon atoms with identical electronegativities. But in this case, because the oxygen is more electronegative, this is not an unreasonable resonance form. It's not as good as this resonance form, the first one. The first one has more bonds, more total bonds, and less formal charges. So that's the better of the two resonance forms. But this is a reasonable resonance form, and it tells us something really important. It tells us that the carbonyl carbon is electrophilic. And that's a big clue with regards to how the molecule will react. So we said we're going to look at hydration. Let's go ahead and do that now. And we're going to look at hydration under basic conditions. Basic aqueous conditions. It's going to have to be aqueous conditions for sure because it's a hydration reaction. Hydration means we're going to add water. So let's take our ketone. And let's put it under basic aqueous conditions. That means we're going to have OH minus and H2O present. We've already established via these simple resonance forms that the carbonyl carbon is electrophilic. Under these basic aqueous conditions, we have hydroxide anion, which is a decent nucleophile. So we have a carbonyl carbon that's electrophilic. We have OH minus, which is nucleophilic. And the nucleophile is just going to attack the carbonyl carbon. Now we're going to have to kick those pi electrons up onto that oxygen in order to avoid a violation of the octet rule. But make no mistake about it, this lone pair, which I'm picking on here, is coming in to form a new bond. Those will be the 2 electrons of the new carbon-oxygen bond that form. Now it's a completely reversible reaction. So what we get is an alkoxide anion here. When the pi electrons kick onto that oxygen, we get an O minus, and we call that an alkoxide anion. And then our OH group is attached down there. Well, all that remains is for a molecule of water, which is the solvent, to come along and donate a proton to that alkoxide anion, and we've now produced the product of this hydration reaction, which, as we discovered last time, is a gem diol. Gem or geminal is similar to Gemini. Both alcohol groups are attached to the same carbon, hence the gem of geminal, gem diol. Now what we discussed in class last time is that this hydration product is not a particularly useful product, at least not from a synthetic perspective, because these equilibria favor reactant. In other words, if I get away from the mechanism here and I just draw the overall equation, so there's my ketone, and I'm going to add H2O. It's a hydration reaction. And I'm going to do it under basic aqueous conditions, which means I've got OH minus around. I draw my equilibrium arrow this way, indicating that the back reaction leading back to aldehyde or ketone is actually favored most of the time. I'm going to get my gem diol. Notice that it doesn't matter if you put the 2 OH groups like this or like this, it's all the exact same thing. But what I'm trying to get at here as we look at the overall equation is that I have indeed added water. There's the hydration part of the story. That was the original molecule. Now I've added water to generate this gem diol, but the equilibrium favors reactant, not product. So the problem is if I tried to isolate, if I tried to pull this gem diol out of solution, the equilibrium would simply reestablish itself. We'd spit out some water and produce aldehyde or ketone. It's a no-win proposition. You're not going to be able to isolate this gem diol very easily. So for that reason, it's not a synthetically useful reaction. But what we learned about aldehydes and ketones, and in particular that there's an electrophilic carbon on that carbonyl carbon, or at that carbonyl carbon, is very important because it tells us where the nucleophiles will attack. So that's hydration under basic aqueous conditions. Let's now explore hydration under acidic conditions once again. So there's my ketone. This time under acidic conditions, I'm going to have water and also H3O plus around. So there's the H3O plus, there's the H2O. Now, that's what I've got. These are acidic aqueous conditions. There's no OH minus under acidic aqueous conditions. So the question is, what is the nucleophile that's going to attack that carbonyl carbon? And the answer is, I don't have a very good nucleophile. There's no OH minus, which is a good nucleophile. H3O plus is not a nucleophile at all. It's electrophilic with its positive charge. So the only good nucleophile, or it's not a good nucleophile, but the only nucleophile period I've got is water. And water is a weak nucleophile, and unfortunately that's not going to do the job here. This carbonyl carbon is not electrophilic enough to attract such a weak nucleophile. So what happens? Under these aqueous acidic conditions, the very first thing that happens in this reaction of this ketone is always going to be the first thing that happens whenever we introduce a carbonyl containing functional group like an aldehyde, like a ketone, like some others that we will study in the near future, like carboxylic acids or esters. Whenever I have a carbonyl containing functional group in the presence of an acid, the very first step is always going to be protonation of the carbonyl oxygen. And the aeroformalism will always look just like that. So that's what we're going to do. We're going to protonate that carbonyl oxygen. That puts a positive charge at the oxygen atom. And that's my protonated ketone. Now I also generate water in the process, so I got lots of water around. Water is the solvent. There's no shortage of water. But I want you to look at this protonated aldehyde or ketone in this case, and recognize that this is nothing more than a resonance form for a carbocation. Very similar to that first resonance form we drew with an aldehyde or ketone. Let me show you that one again. Here it is up here. In this case, however, this is just a resonance form of a carbonyl, a neutral carbonyl compound, and this resonance form has both positive and negative formal charges, so it's not as good as the original resonance form, but it did give us that clue into the electrophilic nature of the carbonyl carbon. The point here is that once you protonate a carbonyl carbon, like we've done here, now we have a formal positive charge, and the question is, would that positive charge rather be on the electronegative oxygen or on the carbon? In this case, this is the better resonance form down here, where we have a full formal positive charge at carbon, because carbon is less electronegative. So what have we done? With one simple acid-base reaction, one simple protonation, we've converted this ketone, which has an electrophilic carbon, but it wasn't electrophilic enough to attract this weak nucleophile water. We've converted it into a carbocation, a resonance delocalized carbocation, which now is a super electrophile, and it will attract the weak nucleophile water. Think about SN1 reactions that we learned in Organic Chemistry 1, where we generate a carbocation by spontaneous ionization of a leaving group, and then a water molecule or other polar solvent molecule can come in and attack the carbocation. This is not quite the same. We don't have a leaving group to generate our carbocation. What we did is we just simply protonated at the carbonyl oxygen. But it does generate a carbocation, and water will attack. And when water attacks, we get a new species. There's the water that just added in. Now present the oxygen as an oxonium ion. So all that's left in order to finish this reaction is to bring in another equivalent of water. There's plenty of it. It's the solvent. Pick up an acidic proton. To give us, once again, our geminal diol. We also regenerate the acid catalyst in that last step, H3O+. You know, I should have noted, and I realize now I didn't do it. I should have noted that in the base catalyzed version of this reaction, which we covered just a moment ago, this last step here to generate the gem diol also reproduced the OH minus, the hydroxide anion. So it is a base catalyzed reaction. You regenerate your base at the end of the reaction. You should go back in your notes and definitely add that in if it wasn't there from our prior class. Here, under the acid catalyzed version, I generate the gemdiol plus, once again regenerate the acid catalyst H3O plus. So these are catalyzed reactions for sure, and that's what they look like. Gemdiol formation. Now if we're looking at the overall reaction here, so this is the mechanism for acid catalyzed hydration of an aldehyde or ketone. Now let's just look at the overall reaction. There's H2O. Once again, even under these acidic aqueous conditions, H3O plus, the equilibrium is going to favor reactant, not product. And that's the same as it was in the base catalyzed version, which means, once again, it's going to be not a particularly useful reaction from a synthetic perspective, but we learned a lot as we studied this. Well, hydration is the first of the reversible reactions we said we were going to cover. There it is, hydration. But we also said, in addition to hydration, we'd talk about acetal forming reactions, and this is brand new. The only difference between hydration and acetal formation is that the acetal will be made from an alcohol rather than water. So when we form a hydrate, we're introducing the aldehyde or ketone to aqueous conditions. When we form an acetal, we're using an alcohol. We're introducing the aldehyde or ketone to an alcohol. We're not going to cover it today in this lecture, but you'll soon be introduced to enamines and imines, and in these cases we will be introducing amines. So you add water, you hydrate. You add alcohol, you make an acetal. You add amines, and you can make either an imine or an enamine, and you'll have to wait a little bit longer for details about those. But let's jump right into acetal forming reactions. And I think what I'll do is I'll just show you an overall reaction. So once again, we're going to start with an aldehyde or a ketone. I've chosen the same looking ketone there, and we're going to add alcohol. Let's choose a different alcohol, R double prime OH. So we've got lots of different R groups here, two different R groups on this ketone, a third R group on this alcohol. It's going to take at least 2 equivalents of alcohol, and we're going to work under acidic aqueous conditions. So I'm going to put a little H plus up there to indicate we're under acidic, and I just said acidic aqueous conditions, but in truth it's not necessarily aqueous. We're just going to work under acidic conditions. So we've got our aldehyde or ketone, at least 2 equivalents of an alcohol, acidic conditions. And that is going to produce our acetal. So this is the structure of our acetal. Look at the alcohol we used was the stuff that had the R double prime, 2 equivalents, and now we see why we needed 2 equivalents, because we add ultimately 2 alcohols to the compound. That R double prime O and that R double prime O came from R double prime OH. The 2 hydrogens plus the original carbonyl oxygen combine to make water as another product of this reaction. So this is an interesting reaction because it actually produces water as the product. It is completely reversible, but it's going to turn out that by managing the concentration of water, we can drive this reaction in either direction. So you're probably familiar with the idea of Le Chatelier's principle. When you have an equilibrium, you can drive the equilibrium in either direction by managing concentrations of species involved. Water is the easiest of the species to manage, so that would be the one we do so. Let's think about this equilibrium. Ketone plus alcohol gives acetal and water. and we're going to try to manage the water concentration. So what could we do? We could remove the water as this reaction proceeds. How could we do that? Well, if we worked at a high enough temperature, for example, we might be able to boil it off. That would be one option. But it turns out, depending upon what these R groups are, this could be very large R groups such that these compounds are not even very water soluble, or maybe they're not water soluble at all. In that case, as we form acetal, the water and the acetal would not mix. They would separate into two layers, and we could simply just remove the water, decant the water as it's formed. And there are even other tricks we can play. It turns out that there are species called molecular sieves, which are like little rocks, almost little pebbles that you can throw into your reaction. Inside these rocks, however, are all sorts of very small pores. The pores are so small that only small molecules, like water, can fit in. And there's things inside the pore which trap the water once it fits in. So it's like a sponge, but it's a sponge that is specific to water. It picks up water, not larger molecules. So we can use these molecular sieves to remove the water from the solution without decanting it, without boiling off the water. There's some other tricks we can play too, but suffice it to say that in the lab, experimentalists have developed a lot of tricks, a lot of procedures to help manage water concentration, and that includes to remove the water as it's formed. So when we think about Le Chatelier's principle, if we are removing this water as it's formed, then we're never allowing the equilibrium to establish, and the equilibrium will be impacted. This external force we're applying, which is basically removing one of the products, is going to drive the equilibrium continuously in that direction to try to make more of that water which is being removed. And if we just continue to remove it, it just keeps going and going and going, and eventually we can produce 100% acetal. So by removing water, we can drive the reaction to completion and make all the acetal we want. What if for some reason we want to go in the other direction? That's easy enough to do too, because now all we have to do is, instead of removing the water, flood the system with water. When we flood it with water, now we've got too much product on this side. The equilibrium will reestablish and start converting acetal back to ketone and alcohol. So this turns out to be pretty useful, and we're going to talk a little bit more about that. The fact that we can selectively push the equilibrium in either direction just by managing water concentration, by either removing the water, or if we want to push back in the other direction, by adding excess water, makes this a particularly useful reaction and a synthetically useful reaction, and we'll see an example of that. Okay, what I want to do now though is I want to show you a real ketone. So let's choose this one, butanone, and we're going to treat it with a real alcohol, let's say methanol, and I've got to have at least 2 equivalents, and we're going to do this under acidic conditions such that we produce the corresponding acetal. So there's my ketone backbone. And now I know I'm going to have these OR groups from the alcohol, and they're just methyl groups. So there's an O-methyl, and there's an O-methyl, and of course water is the other product. So that would be the reaction between this ketone and this alcohol. You'd form the corresponding acetal. Let's see if we can predict the product of a different reaction. What if I had a cyclic ketone like this cyclohexanone, and I reacted it with greater than 2 equivalents of ethanol? And I did that under acidic conditions. Well, in this case, I'm going to produce an acetal in which the carbonyl group is gone, but in its place will be OR, 2 of them, and my R group is now an ethyl, so it'll look something like that, plus H2O as a byproduct. So these are 2 different acetals made in different ways, and we could draw up lots and lots of these predict the product type problems where we start with an aldehyde or a ketone, we react it with at least 2 equivalents of an alcohol, under acidic conditions and then predict the product of the corresponding acetals. Now I've been writing at least or greater than 2 equivalents of the alcohol. Generally speaking, if you're going to run an acetal forming reaction like this with a small alcohol like that, these alcohols would become the solvent and you would just use a massive excess of these alcohols. That also will help to push the equilibrium toward the right because you've got massive amounts of alcohol, and even if you don't remove the water, in that case you're going to form, by Le Chatelier's principle, quite a bit of the corresponding acetals. I'm going to show you the mechanism of this reaction in just a moment, but I want to tell you about an interesting reaction that also forms an acetal. At first glance, it's going to look a little bit different from what we saw. Look at this reaction. I'm going to take this aldehyde or ketone, this happens to be acetone, dimethyl ketone, very simple ketone, and I'm going to react it with 2 alcohols, but this time the alcohols are tied together in the same molecule. This is ethylene glycol. I'm going to still do it under acidic conditions, but the product I'll get out will be OR, OR, and those R's happen to be tied together. In other words, in this case, since I used a diol instead of a simple alcohol, I get a cyclic acetal. And of course, water would also be formed. So all of these reactions, whether you're forming acetals or cyclic acetals, are very closely related, and you're going to see they all follow the same mechanism. It doesn't really matter if both alcohols came from the same molecule, or if in the case of an ethanol, we just use 2 ethanols to put the OR groups on. It's all the same kind of product, except that when we use a diol, the acetal is cyclic because the 2 alcohols are tethered together. Let's do a predict the product problem. Let's go with a benzaldehyde. So there's an aldehyde. And now I'm going to treat it with a diol. This one has 3 carbons in between the 2 alcohols. This one is called a propylene glycol. And we're going to add those together under acidic conditions. There's my aldehyde, so I'm going to form OR-OR in place of that carbonyl oxygen. Let me go ahead and draw that in. I'll still have that bond to hydrogen, that's not going to go anywhere. There's the first O, there's the second O, and then these 3 carbons tie them together. So this is another cyclic acetal. This cycle's a little bit bigger because I used propylene glycol rather than ethylene glycol. And of course I still generate H2O. So whether it's a regular acetal or a cyclic acetal, we can run these reactions quite effectively, and because we can manage the water concentrations, we can make high concentrations of these acetals, the cyclic acetals as well as the regular acetals. All right, let's look at the mechanism. So mechanism of acetal formation. And we've got to choose a representative reaction to do this with. Let's go ahead and choose an aldehyde. I'm going to choose propanal. And let's choose an alcohol like methanol. And we know that we're going to have greater than 2 equivalents. We can predict the product already, so we're drawing out the overall reaction here. We know that we're still going to have our backbone of our aldehyde, but in place of the carbonyl group, we're going to have OR twice. And since R is just a methyl group, we'll just have 2 of those. And of course, we'll also produce water. So this will be the overall reaction. Now for the mechanism. We're working under these acidic conditions, and A few moments ago I told you that whenever you work under acidic conditions, the first step will always be the same. Your carbonyl oxygen will be protonated by the acid to generate this protonated, in this case aldehyde. But we know that once you protonate that carbonyl oxygen, what you've really produced is a resonance delocalized carbocation, and this resonance form really looks like a carbocation. And it's the more important of the two resonance forms because it places the positive charge at the less electronegative carbon. So there I've just protonated my aldehyde or ketone to generate this resonance delocalized carbocation, a protonated aldehyde. Now, I'm not being very specific about what my acid is here, which is why it's okay in this case just to write H+. We know as well-trained organic chemists that H+, the proton, doesn't exist in solution as such, but it turns out when I run a reaction like this, I could use, for example, a couple drops of sulfuric acid or perhaps phosphoric acid. I've got some choices with regards to the acid that I use, so I'm being very generic about what that is. If we were drawing this out with sulfuric acid, the aeroformalism would be a little bit more extensive, but not a whole lot more. In the end, we would be delivering a proton just as this aeroformalism indicates. We generate this resonance delocalized carbocation, and this is all done in the presence of our alcohol. Now, the alcohol itself is not acidic enough to cause this protonation, but it is present. The alcohol is present, there's no doubt about that. And so once we generate this carbocation, my alcohol is a lot like water. It's a weak nucleophile, but next to this super electrophile, it is quite attracted. So we're going to have an equilibrium formation of a new species. It looks a bit like that gem diol, only this is a methyl group up here because it came from methanol. So I've generated an oxonium ion, very, very similar to what happened during hydration. If I go back to that mechanism of hydration that we just constructed a few moments ago, look at what happened here. Here was our ketone. We treated it with H3O+, an acid, to generate an oxonium ion. There's the resonance form where we see it looking like a carbocation. Water, not an alcohol, but water came in order to generate this species. And look at that species and compare it to this one. Looks very similar. The next step, we've got lots of alcohol around, and our alcohol is going to come in and pick up that acidic proton in order to give us this species right here. This species is not a gem diol. You see it's an OH and an OR. And we refer to this species, it's sort of halfway between a gem diol and where we're headed, which is the acetal, where we have two OR groups. Right now we only have one OR group on board. We refer to this as a hemiacetal. It's like halfway to an acetal, but we're not quite there. This step also generates more acid. See, our alcohol picked up an acidic proton and we generate CH3OH2+. This is like H3O+. This is an acidic species. It's a protonated alcohol. So this reaction is catalytic. We're regenerating acid as we go. Let me draw that same species out. This is the same thing. I'll even put the CH3 group on there so it's clear that that's the same species, but I've got now the oxygen-hydrogen bonds drawn out. And you can see that it looks a lot like H3O+, and it's going to behave just like H3O+. Now what will it do? One thing it could do is it could protonate this oxygen of this OCH3. That would actually take us right back to here. if we used an arrow formalism that looked like this, picked up the acidic proton, we'd go right back to here. We know that happens. This is a reversible reaction, which means we can traverse back and forth throughout. But if we want to go in a new direction toward the acetal, then there's another equilibrium which will be at play, and that one will involve taking one of these lone pairs right here and using them to pick up an acidic proton. And when we do that, then I have generated OH2+. I've generated water as an oxonium ion. And one thing we know about water as an oxonium ion is that it's a good leaving group. It can leave as water, and when it does, we generate a carbocation. This carbocation is once again going to be attracted to even weak nucleophiles. I just drew water because I eliminate water in this step. So it is possible for water to hop on that carbocation. That would take me right back to where I was. But there's only one water molecule in this whole solution so far. That's the one I just generated. There's lots and lots of alcohol. So it's much more likely to interact with our solvent, the weak nucleophile methanol. And when that happens, we're going to have to go on to another page here. When that happens, I generate one more oxonium ion, which looks like that. And once again, another molecule of methanol. I'm using it in excess, so there's plenty of it. Is going to come along, and this time it's going to give me my final product, which is my acetal. I also regenerate another acid. So every time I use an acid, I regenerate one in a subsequent step, hence the catalytic nature of this reaction. So there it is. There's my acetal. Notice that along the way, we did indeed form one and only one molecule of water. So if I go back to the overall reaction, which is listed here, I have an aldehyde or a ketone, in this case an aldehyde, propanal, reacting with an alcohol, in this case methanol, under acidic conditions. I'm going to put two of these alcohol groups on that carbonyl oxygen. I'm going to get rid of that oxygen. It's going to leave right there as water. OCH3, OCH3 taken twice. That gives me my acetal structure. Both of those protons plus that oxygen result in that water right there. There's only one water molecule produced for every one acetal that's produced, and that's why managing the water concentration is such a critical component here. We don't have a huge excess of it, so it's not as challenging to manage as if it were the solvent, for example. It's not the solvent. In all likelihood, my alcohol is the solvent. I write here greater than 2 equivalents. Being the solvent, you're going to have a massive number of equivalents. So that's how we run the reaction. At the end of the day, there's my acetal. Okay, so we've looked at the mechanism for formation of an acetal, and let me emphasize that this mechanism does not change when we go to a cyclic acetal. So I showed you some examples of cyclic acetal forming reactions. Here's one right here. Here I take a ketone. This one happens to be cyclohexanone. I add at least 2 equivalents. Probably it's the solvent, so there's trillions and trillions of equivalents of alcohol, ethanol in this case, under acidic conditions. We're going to get rid of the oxygen and 2 hydrogens when we bring in 2 of these alcohols, O-ethyl, O-ethyl. The 2 hydrogens and the oxygen of the carbonyl go to form water right there. Sorry, this one wasn't a cyclic acetal forming reaction. This is just a regular acetal. It looks cyclic to me from a glance because I started with a cyclic ketone. But the cyclic acetal, where the acetal functional group is cyclic, would require a diol, like this ethylene glycol or this propylene glycol. In this case, same reaction, carbonyl 2 alcohols, at least 2. Once again, I'd use a big excess of the diol. Might even use it as my solvent under acidic conditions. 1 alcohol, 2 alcohols are going to add in. They happen to be tethered together. That oxygen and those 2 hydrogens form water. The mechanism is identical even in this case where you're forming a cyclic diol, a cyclic acetal. So let's do some predict the product problems and ultimately talk about how we could use this acetal forming reaction in a synthesis problem. But first, predict the product problems. So let's go to a ketone. In this case, it is a 1,2-pentanone. And let's add some cyclic diol. Let's go with ethylene glycol under acidic conditions, and let's predict what the acetal product would look like. We know in an acetal forming reaction we're going to add 2 alcohols. This time they happen to be on the same molecule because it's a diol that we're using. And so the first alcohol will add in. Eventually we'll spit out water. The second alcohol will add in. There's the first, there's the second. They're tied together by a 2-carbon bridge. There's the 2-carbon bridge plus H2O. So that's what my cyclic acetal would look like in this case. All right, let's go to an exotic molecule. This is an aldehyde now, tethered to an alkyl group and eventually a benzene ring back here. None of that really matters. This is just a big R group for our purposes. It's this part of the molecule right here, the aldehyde functional group, that's going to be reactive. Let's go ahead and add 3 carbon alcohol. This will be propanol, 1 propanol, and we know that we need at least 2 equivalents. Once again, we're in all likelihood going to be using this as our solvent, so there'll be many more than 2 equivalents. It'll be trillions and trillions of equivalents, and we're going to run this under acidic conditions, which is required. The mechanism will pass through that hemiacetal and eventually go all the way to the acetal. What's that acetal going to look like? I'm going to draw it down here. Going to have that benzene ring, and we've still got our backbone associated with our aldehyde here. If I was drawing the aldehyde, I'd draw a carbonyl group right there, but in its place will be 2 OR groups, and this time the R is a 3-carbon alkyl unit, propyl. So there's my acetal plus H2O. So we can make truly many, almost an infinite number of different acetals, starting with many different structural types of aldehydes and ketones. We can make cyclic acetals, we can make standard acetals, we can do all sorts of things here. Now, let's look at a synthesis problem where this might come in handy. Let's say I had this aldehyde right here. Now what I want you to notice about this aldehyde is it's actually got another functional group on it. This is an alkyl iodide on this end and an aldehyde on that end. And let's say that I was thinking about the good old days of Organic Chemistry 1 and SN2 chemistry, and I wanted to run an SN2 reaction involving a good nucleophile. This is one of my best, cyanide, right here at this primary carbon. Looks like it should work beautifully. I've got a good SN2 substrate, a primary iodide, an excellent nucleophile. Looks like I should have no problems whatsoever to produce the cyanide plus the iodide anion as a leaving group. Well, it looks great, but we do have a problem. This molecule, unlike what we saw in Organic Chemistry 1, doesn't just have a good SN2 substrate on it, it's got an aldehyde on it, and as we've been talking, the carbonyl carbon of an aldehyde is also electrophilic. And so actually one of the reversible reactions that aldehydes and ketones will undergo is it will react with cyanide anion. Let's look at that reaction. So there's my cyanide anion. A good nucleophile will attack this electrophilic carbonyl group. And when it does, the arrow formalism would look like this. We'll kick the pi electrons onto the oxygen. And look what happened. We've added the cyanide anion. We're probably running this in water because we need a solvent that will solubilize this cyanide, which is probably present as a salt, must be present as a salt. Maybe it's a potassium cyanide or a sodium cyanide. I haven't shown the countercation, but there has to be one. And so let's just go ahead and show one. If we used potassium cyanide, then we could say we used that up here. Instead of just producing the iodide anion as the leaving group, it would have been potassium iodide. There's always a countercation for any anion. Here I would have used potassium cyanide, and now the potassium would just be associated with this alkoxide. That might be the end of the story, but as I said, we're probably in water, and it is certainly possible that this alkoxide will then just be protonated to produce this compound right here, which is known as a cyanohydrin. So this is a reversible reaction. Actually, this reaction is sometimes used as a test for aldehydes or ketones. If cyanide anion is reactive to produce something like this cyanohydrin, then you know you have an aldehyde or a ketone present. Well, bottom line is, what I'm looking at here on this page are two reactions. Because this compound I started with is bifunctional, the cyanide anion can undergo an SN2 reaction, which might be the one I was trying to run, but it can also undergo this cyanohydrin forming reaction here. So what do? How do I direct the chemistry to the SN2 path? That's what I really want. I want to form this product. I don't want this cyanohydrin. My issue is I've got two different electrophiles. The electrophile here, this carbon attached to the good leaving group, the electronegative halogen, making it electrophilic, and the electrophilic carbon of the carbonyl. So here's what I would do. I would use the chemistry that we just studied, namely acetal forming conditions. Watch this. I'm going to redraw the starting compound. There's my aldehyde. And what I want to do is I want to protect that aldehyde group, meaning I want to disguise it. I want to make it appear as though it's not an electrophilic carbon right there, so that I don't have to worry about this extra cyanohydrin forming reaction. And the way I'm going to do that is I'm going to use acetal formation. And I'm choosing here to produce a cyclic acetal by virtue of the fact that I'm using ethylene glycol under these acidic conditions by managing the concentration of water. Remember, water is also a byproduct. I can selectively produce this cyclic acetal. I'm going to manage that concentration of water in order to drive production of this cyclic acetal. There it is. Now that I've got the cyclic acetal, that's no longer a carbonyl carbon, and it's not going to be reactive with cyanide anion. So now I can bring in a separate second step, the cyanide anion, and do the SN2 chemistry that I wanted to do right at the carbon atom where I wanted it to take place. There it is. Now this SN2 reaction is not complicated by simultaneous addition of the cyanide to the carbonyl carbon, because there is no carbonyl carbon. I have protected the carbonyl carbon by converting it temporarily into this acetal. But here's the great thing. We've been talking about these reactions being reversible. Here's a perfect example. Two perfect examples of prior reactions we looked at. Let's just look at the top case here. This 2-pentanone plus ethylene glycol under acidic conditions, reversible. My arrow is a little funky there. Reversible conditions. I get the cyclic acetal in this case, a regular acetal down here, a cyclic acetal up here, it doesn't matter, plus H2O. By managing the water concentration, I can pull out the water and drive a reaction toward the acetal, but I can also drive it in the opposite direction. I can flood the system with water and by Le Chatelier's principle drive all the acetal back to aldehyde or ketone as long as I'm under acidic conditions. So that's what I'm going to do right here. I've produced this cyclic acetal in order to protect the aldehyde group so that I could run the SN2 reaction as I wanted to. But now I'm going to deprotect. So I'm going to go in, I'm going to add lots and lots of water under acidic conditions. Whoops, that's H3O plus H2O. Lots and lots of water under acidic conditions. And I'm going to drive, by Le Chatelier's principle, that equilibrium right back to aldehyde. And I'm not going to show you the mechanism. It would be the reverse of a hydration mechanism that we've already covered, but there it would be. This last step is taking advantage of the fact that we can manipulate this acetal reaction beautifully by managing water concentration and taking advantage of Le Chatelier's principle. Now look what I've done. I've converted the cyclic acetal back to an aldehyde, and I have the cyanide exactly where I wanted it, without the complication I had before. This was the earlier attempt, not very successful. I didn't protect the aldehyde, so in addition to getting some SN2 chemistry, which is what I wanted to occur, I also produced the cyanohydrin, and I didn't want that to occur. But now, by first protecting the aldehyde as a cyclic acetal and then running the SN2 reaction, I produce cleanly this product, which then I take the cyclic acetal and drive it back to the aldehyde using an excess of water. It's a beautiful way to do synthesis. We call this type of process where you protect a functional group, we call that protection. And then later on, when you want to take off the protecting group, we call that deprotection. So what we've just done is we've seen an example of a protection deprotection sequence, and these are the types of sequences which are used routinely in organic synthesis. The modern organic chemist does this all the time, not just with aldehydes and ketones, but with many other functional groups as well. Because the truth of the matter is, most of the interesting compounds that we encounter that we want to do chemistry on do have more than one functional group present. And sometimes the chemistry we want to do is complicated by the fact that it'll do other things we're not interested in.